In this video, we're going to talk about systems of linear inequalities in two variables. So we've talked about systems of equations. A system of equation is just a set of equations that defines a relationship among the variables in a problem. Well, a system of inequalities is just a set of inequalities that defines a relationship. So we're going to think of these inequalities as constraints, in other words, limitations. So a constraint is something that places restrictions on the values the variable can take on. So variables don't have to be exactly equal to something, but they typically have to be less than something or they have to be greater than something. So we're going to think of these as constraining the values that our variables can take on. Now, if a situation is subject to multiple constraints, in other words, multiple limitations, we can often represent it using a system of inequalities. So graphically speaking, the solution to the system is going to be given by the intersection of all of the graphs. So we talked about how you'd solve a single linear inequality by graphing. We graph a boundary line, so we imagine the inequality with just an equal sign instead of an inequality sign. That gives us a line, so we graph that line in the coordinate plane. And then the actual inequality part corresponds to one of the half planes that's divided up by that boundary line. So either something to the left of that line, something to the right of that line, depending on the inequality sign we have. Now, if we have more than one linear inequality, in other words, we have a system of inequalities, what we're looking for is where all of those solution regions overlap. So if we graph all the inequalities on the same coordinate plane, we're looking for where the shaded regions overlap. We're looking for the intersection of our graphs. We call this the solution region for our system, or the feasible region. In other words, every ordered pair that's in the shaded region, that overlapping shaded region, is a possible solution to our system. It represents a combination of values that our variables could take on that would solve our system of inequalities. Now, to keep things simple, we're only going to consider inequalities of the form less than or equal to or greater than or equal to. We know with those particular inequalities that we include the boundary line as part of the solution. So using inequalities of that type is just going to make our lives a little bit easier, so we don't have to worry about issues related to whether or not the boundary line is part of our solution. So any point in our solution region, if we want to go point by point, individual ordered pair by ordered pair, we have to make sure that that particular combination of values satisfies all the inequalities in our system. So if we can find an ordered pair that satisfies one inequality but doesn't satisfy another, then we know it's not an actual solution to our system. It has to satisfy every inequality in the system. So let's look at an example. So we want to determine whether or not each of these ordered pairs is in the solution region for this system of linear inequalities. So our system is 4x plus y is less than or equal to 20, 3x plus 5y is less than or equal to 37. So those are the two inequalities that define the relationship between x and y. And then we also have two additional inequalities. We have that x is greater than or equal to 0 and y is greater than or equal to 0 as well. Those last two inequalities we call non-negative constraints. All those are telling us is that the values that we choose for our variables cannot be negative numbers. They have to be at least 0. So we've got three ordered pairs. We want to determine which, if any, of these ordered pairs are solutions to this particular system of inequalities. And again, keep in mind when we talk about an inequality, we typically have a lot of possible solutions. These are just individual possible solutions that we might have. So our first ordered pair is going to be 3, 5. We want to determine if this is a possible solution to our system. So in order to make this determination, we have to verify that the ordered pair 3, 5, were we to substitute it into our inequalities, gives us correct, true inequalities. So I have to substitute that into all of my inequalities. It has to make them all true in order for this ordered pair to be a solution to our system. So the easiest ones to check are going to be the non-negative constraints. We know that x and y both have to be greater than or equal to 0. In this case, both x and y are greater than or equal to 0, so those last two inequalities we know for sure are satisfied. We do need to verify, though, that the first two inequalities are satisfied. So I'm going to substitute my values for x and y into these two inequalities, and I want to determine what happens. In other words, do I end up with a statement that's true? Do I end up with a statement that's false? So I'm going to sub into my first inequality, sub in 3 and 5. So we have 4 times 3 plus 5. In other words, 12 plus 5, which gives me 17. And according to the inequality, that's less than or equal to 20. Well, that's a true statement, so that inequality is satisfied. We also need to verify that the second inequality is satisfied, so I'm going to do the same thing, but I'm going to substitute into that second inequality. So we have 3 times 3 plus 5 times 5. So 3 times 3 is 9, 5 times 5 is 25. We add those two together, and we end up with something that's less than 37. So that inequality is also satisfied. So this combination of values for x and y works in all 4 of these inequalities we have in our system. So that's our indication that 3, 5 is one point in our solution region. Keep in mind, it's not the only point, but it is one point that's in our solution region. Let's look at another ordered pair. So what about the ordered pair 4, 5? Well, we can immediately verify that our non-negative constraints are satisfied, so that's good. We also have to check the first 2 constraints though, those first 2 inequalities. So I'm going to sub into my first inequality. So we have 4 times 4 plus 5. Well, 4 times 4 is 16. 16 plus 5 gives me 21. So based on this inequality, I'm saying 21 is less than or equal to 20. Well, that's definitely a false statement, which means that this ordered pair does not satisfy one of the inequalities in the system. Because it doesn't satisfy one of the inequalities in the system, automatically we can say that it's not a solution to the system of inequalities. We don't actually have to check the other inequality. Once we find one that's violated, it doesn't matter what happens with the rest of the inequalities. We can move on and we can immediately say that that's not a possible solution. Now let's check one more. So we have 3, 6. Again, our non-negative constraints are satisfied. We also need to plug into our original 2 constraints, the ones that give us the relationship between x and y. So I'm going to plug into the first inequality. I have 4 times 3 plus 6. So 4 times 3 is going to be 12. 12 plus 6 is going to be 18. So based on that first inequality, we're saying 18 is less than or equal to 20. So that is a true statement. So the first inequality in the system is satisfied. Now we need to check the second inequality. So using the second inequality, 3 times 3 plus 5 times 6. Well, 3 times 3 is going to give us 9. 5 times 6 is going to give us 30. 9 plus 30 is going to give us 39. And then based on our inequality, we're saying that 39 is less than or equal to 37, which in this case is a false statement. So the first inequality is satisfied, but the second inequality is not. So we can conclude that the ordered pair 3, 6 is not a solution to our system of linear inequalities because it does not satisfy all the inequalities in the system. So that's a way we can check individual ordered pairs. If that's the goal, just to check individual possible values, we can do that by hand. Well, what if we want to determine all the ordered pairs that represent our solution? In other words, all the different values that our variables can take on. At that point, we're essentially going to do what we did before with the individual inequalities. We're going to graph the inequality, but in this case, we're graphing more than one, and we're looking for locations where those graphs overlap. Any location where our graphs overlap represents a location where we have solutions to our system. So let's look at some examples. First off, we need to define some terminology. So a corner point is going to be any point in the solution region that is the intersection of 2 boundary lines. So in other words, if we're defining a region in the coordinate plane that represents possible solutions, it represents one of the corners in the region. It's a key location where specific things happen, and it's going to occur wherever boundary lines intersect. Now, once we have our solution region, that overlapping shaded region, we can say the solution region is bounded if we could draw a circle around it. In other words, if it's a finite amount of space. Otherwise, if it's such that we could not do that, we couldn't actually confine it into a circle, we would say that the solution region is unbounded. In other words, it continues forever and ever in maybe 1 or 2 particular directions. So let's look at a few examples. So we want to solve each system of inequalities by graphing. We also want to find the coordinates of each corner point, and we want to determine whether or not the solution region is bounded. Now this can be done by hand. So we talked about how we would graph an individual inequality last section, what that would look like. Remember, we draw the boundary line and then we pick a test point that's going to tell us what side of the boundary line to shade. We would have to do that for each of the inequalities in the system. There's actually a great tool to help minimize some of the time it takes to graph. It's called Desmos.com. So it's a free graphing calculator that you can use online. I'm going to show you how to use that in another video. So we're just going to talk briefly about what the graphing would look like, and we're just going to interpret from the graphs we have, and then I'll show you in another video how you could graph this using that piece of software. Okay, so for our first system, we have x plus y is greater than or equal to 6, and 2x minus y is greater than or equal to 0. Okay, so we need to graph both of these inequalities, and what we're looking for is where those graphs would overlap. So if I were to graph these by hand, remember I'm going to pretend for just a minute that each of these is an equation. So I'm going to take my inequality signs, both of them are greater than or equal to. I'm going to replace them with equal signs. That gives us the two boundary lines in this particular graph. So we have a boundary line at x plus y equals 6. We have a boundary line at 2x minus y is equal to 0. Well, say I wanted to graph these by hand. Remember, an easy way to do that would be with intercepts. So for that first line, if we let x be 0, we know that y would have to be 6. If we let y be 0, we know that x would have to be 6. So this particular line is represented by two intercepts, both at positive 6. So we could draw that boundary line pretty easily. If we were to choose a test point, we would end up shading the upper side of that line, so the upper half plane. Now we need to do the same thing for the other line, the other boundary line. Again, we could use intercepts if we want. As it turns out, both intercepts are going to coincide at the origin, so we would need an additional point. Another point that's going to be on this line happens to be that corner point that we find. So if we were to allow x to be 2, for instance, we would have 4. So 2 times 2 would give us 4. That means y would have to be 4 in order to satisfy that equation. So another ordered pair on the line would be 2, 4. And it just so happens that that's going to be the location where there's two boundary lines intersect, and we call that a corner point. So if we were to graph that boundary line, so here's the line, and then use a test point to determine what happens with that particular inequality, then we would end up shading the half plane that's below that boundary line. So we have a half plane shaded here, we have a half plane shaded here, so the overlapping region is this region right here in the upper right-hand corner in the first quadrant, going down a little bit into the fourth quadrant. And we have a single corner point at the ordered pair 2, 4. So that's going to be the corner point that defines that particular region. Now notice it looks finite just based on what we have drawn right here, but this is just one small snippet of the coordinate plane. It's not the entire coordinate plane. So we have to keep in mind that our graph continues up and to the right, and also down, outward, forever and ever and ever and ever. So this particular solution region is actually unbounded. We could not draw a finite sized circle around this region to enclose it all. So we would say that this solution region is unbounded. Okay, so let's look at another one. X minus 2y is less than or equal to 12. 2x plus y is greater than or equal to 4. So again, if we were going to graph by hand, we start by converting these to equations. That gives us our two boundary lines that we draw. We draw our two boundary lines. In this case, we can note that those two lines intersect at the ordered pair 4, -4. We shade based on a test point. So neither of these lines passes through 0, 0. So we could use 0, 0 as a test point for each of these two inequalities. 0, 0 actually satisfies neither of those inequalities. So we end up shading to the other side of those particular lines. And in this case, the overlapping region is again going to be the region in the upper right-hand side of the coordinate plane. So we have a corner point at 4, -4, and we're shading the region bounded by that in the upper right-hand corner. So anything in this region represents a solution to our system. Yet again, this is an unbounded solution region because it's going to continue forever and ever, up and out. So we know we can't draw a circle around it. We know it's going to be unbounded. Okay, so both of these systems have two inequalities and they resulted in unbounded solution regions. Let's add on a couple more inequalities and see what happens to the situation. So for the next example, we have 4 inequalities. We have 2 inequalities that look very similar to the ones we had, but then we also have some non-negative constraints. We have x is greater than or equal to 0 and y is greater than or equal to 0 as well. What these 2 non-negative constraints tell us is that our graph is going to be confined to the first quadrant. So x greater than or equal to 0 and y greater than or equal to 0. Well, the only location that occurs in the coordinate plane is in the first quadrant and then there along the y-axis and the x-axis bounding that first quadrant. So we're going to graph the 2 first linear inequalities just like we graph any other situation. But because of these non-negative constraints, what we shade is going to be restricted to the first quadrant. So we take both of those 2 original inequalities, write them as equations, convert them to equations. Those represent our boundary lines. Again, we can graph using intercepts. That's a good option. These 2 lines, if graphed, intersect at the point 2, 4. So that's going to be where those 2 lines intersect. Now, with the previous examples, we only had that one corner point where those 2 lines intersect, but we also have to consider the fact that x greater than or equal to 0, y greater than or equal to 0, those have equation forms as well, and those represent boundary lines as well. So x greater than or equal to 0 would convert to x equals 0. X equals 0 is a vertical line. Specifically, it's the vertical line that we call the y-axis. Now, y greater than or equal to 0, if we convert that to an equation, that's y is equal to 0. That is a horizontal line, specifically the horizontal line that we call the x-axis. So we actually have 4 lines defining our region in this case. We have the 2 diagonal lines that we got from our first 2 inequalities, and then the non-negative constraints actually represent the x and y axis. But we're looking at the portion defined by the first quadrant when we draw those lines. So what that does is it adds on additional corner points. Any location where a pair of lines intersect represents a corner point. So we have that corner point at 2, 4 where the 2 diagonal lines intersect, but we also have a point where we intersect with the y-axis, where we intersect with the x-axis, and then also technically those 2 lines, x equals 0, y equals 0, those 2 lines intersect at the origin. So that's also a corner point. So in this case, we end up having 4 corner points that define our region. Now notice based on our shading and based on the corner points, how they define that region, this region is actually going to be bounded. So we could draw a large enough circle to enclose this entire area. This entire area does not continue, it's confined to that one small space. So that means that this solution region is going to be bounded. Any solution we want has to be an ordered pair in that region. So there are infinitely many points in that region, but all the points we have as part of our solution are going to stay confined to that small space. Okay, let's look at one more and then we'll look at an application. So now we actually have 5 inequalities. It's okay, that just means we're going to graph 5 boundary lines and we define our region from there. So our first 3 inequalities define the relationship among x and y, and then the last 2 inequalities are going to be our non-negative constraints. So again, when we graph this particular set of inequalities, we're going to confine our graph to the first quadrant because we know x and y have to be non-negative numbers. So I graph my 3 boundary lines. I choose a test point that's going to tell me what side of the lines to shade on. That's going to define the actual shaded region. And then I want to look for those locations where my lines intersect. In other words, where I have corner points. So I have the 3 diagonal lines defined by my equation forms of my inequalities. I'm looking for where those intersect. And then I also have the vertical line along the y-axis, the horizontal line along the x-axis, defining our space as being constrained to the first quadrant. So I have a corner point at the origin where the vertical and horizontal line intersect. I have a corner point on the x-axis, and on the y-axis were those diagonal lines. Notice it's the lowest diagonal line and the furthest left diagonal line that define the actual corner points at those locations on those axes. So those are going to be additional corner points. So we have a corner point at, looks like 5, 0, and then looks like 0, 6. Those are also corner points. And then we have 2 additional locations right there where 2 boundary lines intersect. One of them is going to be at 2, 5, and the other one is going to be at 3, 4. So it's hard to see. That's one thing that Desmos is going to be great for. It's going to allow us to zoom in and see what's happening in this kind of location where things are a little bit muddy. But we actually don't have a straight line right here. We have a segment, another diagonal segment, and then a third diagonal segment defining the shape of this region. So 1, 2, 3 diagonal segments defined by 1, 2, 3, 4 corner points, and then the additional corner point there at the origin. So any ordered pair represented by that solution region is a solution to my system of inequalities, and it's bounded by that particular set of lines and that particular set of corner points. So this is an actual bounded solution region. It's enclosed fully. We could draw a circle around it, so we know that solution region is going to be bounded. So we'll take a couple of the examples in this particular section, the ones we just graphed, and I'll show you what that looks like on Desmos. Again, Desmos is going to be a great tool for you to use. It's going to make your graphing quite a bit easier. It's going to make it go a lot faster. Okay, let's look at an example of how we would use a system of inequalities. Now, there are a lot of different situations we'll use these for. We're actually going to talk about a type of problem called a linear programming problem, where we have several different things we have to work together with that end up being represented by inequalities, but we'll get there. So let's look at a basic situation first. So here's our example. A patient on a specialized diet is required to have at least 800 calories and at least 32 grams of protein per day. Okay, so each serving of food A contains 200 calories and 5 grams of protein. Each serving of food B contains 80 calories and 8 grams of protein. What we want to know is how many servings of each food should be eaten per day to meet the minimum daily requirements. Now notice it does say minimum daily requirements. What are those? Well, the minimum requirements are that we have 800 calories, in other words, at least 800 calories, and at least 32 grams of protein. So say, for instance, we have some combo that gives us 900 calories and 35 grams of protein. Well, that's fine. The goal is just to meet the minimum and potentially surpass it. Since we don't have an exact requirement, it doesn't say we have to have exactly 800 calories, exactly 32 grams of protein, that's our indication that this situation is represented by inequalities. We can pass those amounts, we just have to make sure we at least meet those amounts. So in a situation like this, where there's a lot of different components, we need to be really organized. So I've drawn a table. I want to organize based on nutrients and then based on food types. So calories and protein in food A and in food B. So food A has 200 calories and it has 5 grams of protein. So that's everything for food A. Now food B has 80 calories and 8 grams of protein. So that's going to be everything in food B. The last column represents those minimum requirements for this particular patient. So we know the total amount of calories needs to be at least 800, and then the total amount of protein needs to be at least 32 grams. So we have all the information that we were given organized in table form. Now we need to think about what we want to know. So the question was, how many servings of food A, how many servings of food B should be eaten in order to meet these requirements of 800 calories and 32 grams of protein? Okay, so once I know what I'm looking for, that's going to tell me what I'm going to define as my variables. So I have 2 different types of food. I'm going to eat different combinations of those 2 types of food. So that's going to represent my variables. So I'm going to let X represent how many servings of food A that I assign this person. And I'm going to let Y represent how many servings of food B I assign this person. Think about this kind of like revenue problems. So we've done several revenue problems sales problems. We're selling a certain amount of something that's worth a certain amount or that we charge a certain amount for. Whenever we want total sales, we take the price we charge and multiply it by how many items we sell, and that gives us that portion of sales. This is actually the same kind of thing. We're just not talking about dollar amounts in sales. We're talking about nutrient amounts and servings. So in terms of contributing towards the total calories, some of our calories are going to come from food A. Some of our calories are going to come from food B. Okay, so if we were to take the number of calories in food A and multiply it by how many servings of A we have, that's going to be the portion of the total contributed by food A. So say, for instance, we have 1 serving. Well, that would give us 200 calories. If we have 2 servings, that gives us 400. 3 servings would give us 600, and then so on and so forth. So 200 times the number of servings we have is going to be that portion of our calorie content. Now, same thing for food B. So if we have 1 serving of food B, that would give us 80 calories. 2 servings would give us 160. 3 servings would give us 240, so on and so forth. So if we were to take 80 times the number of servings we have for food B, that's going to be that portion of the total contributed by food B. So 200 times X, 80 times Y, add them together since they both contribute towards the total. And because we have a minimum daily requirement, in other words, we want to meet it and possibly pass it, that means we want that total from those 2 different foods to be at least, in other words, to be greater than or equal to 800. So this first inequality is going to represent how we meet that calorie goal. Okay, now we need to do the same thing for protein. So we have different protein contents for each of these types of foods. We know we need to meet that minimum daily requirement of 32 grams. So 5 grams of protein in food A multiplied by how many servings of food A we have. That's that portion of the total of 32. 8 grams in food B times the number of servings of food B. That's going to be that portion of the total. If we combine those together, add them together, we know that we need to meet and possibly exceed the daily requirement. So if we add those 2 together, it has to be greater than or equal to 32. So those are going to be the 2 inequalities that define the relationship among everything that's been defined in the problem statement. Now, 9 times out of 10, when we're talking about a real situation, we're going to have to also add non-negative constraints. What does that mean in this case? Well, based on what X and Y represent, we're thinking about content. We're talking 1 serving, 2 servings. Maybe we could have half a serving. That's a possibility. But we couldn't have any negative servings. Negative servings doesn't make sense in a situation like this. So what that tells us is that the values that X and Y take on have to be greater than or equal to 0. They could be equal to 0 in the sense that maybe we only eat food A, or maybe we only eat food B, which would mean that the other variable would take on a value of 0, but they just can't be negative. So we have to add on those 2 non-negative constraints to make sure that we're only choosing values for X and Y that actually make sense in the context of this problem. Okay, so now I have 2 inequalities. I want to graph those inequalities, also applying those non-negative constraints. So the first inequality, notice it has quite big numbers. I can actually divide out a common factor of 20 among all of the constants in that equation. So that would give me 10x plus 4y is equal to 40. I can find intercepts, a y-intercept of 10, an x-intercept of 4, based on substituting the opposite variable as 0. And so that's going to give me ordered pairs I can use to graph that particular line. So that's going to be that particular line represented as the boundary line of that first inequality. Now, same thing for the other one. 5x plus 8y is now equal to 32 in order to define that boundary line. So our intercepts are going to be a y-intercept of 4, and then notice the x-intercept, it has a decimal as part of it. We can't actually write it as a whole number. That just means when we graph that point, it's going to be graphed between the units. That's okay. In general, these graphs are sort of roughly indicative of the actual region we're defining, so it doesn't have to be super accurate as long as we can algebraically show what numbers we've graphed. So I can graph those intercepts Again, I can use a test point to determine which side of those boundary lines we're going to shade for each of those inequalities. And in this case, we end up shading the region that's above, the region that's in the upper right-hand corner of the coordinate plane, but again, restricted to the first quadrant because of those inequality signs. So this is going to be an unbounded region. Now keep in mind, we're saying there's a minimum daily requirement of 800 calories, 32 grams of protein. More than likely, we probably wouldn't want this person eating, for instance, 10,000 calories a day. So if we were to go a little bit further, we might have some restrictions that give us an upper limit on how high the numbers can go. But just based on the problem description we have, any ordered pair in this solution region, which continues up and continues to the right, as long as we're confined to that first quadrant, any ordered pair in that solution region represents an ordered pair that solves this system of inequalities.